Welcome to the lab. Give everybody a moment or two here. And again, for the majority here, what we're going to do here at the beginning is really just continue lecturing. But we'll talk a little bit about, again, the pH and hydrolysis experiment, just make sure everybody's on the same page before we get to that. And we'll start just a minute or so. And like always, again, if you have questions, feel free to ask them in the box there. And like I said, I'll get to them for sure. Okay, so I guess before we kind of continue on lecturing where we left off, let's just talk a little bit about the pH and hydrolysis experiment that was posted earlier in the week. Again, it's up there. You will need to kind of go through it, much like the equilibrium one. So there's a bunch of different sort of parts in one module all by itself on Canvas. And really the pH and hydrolysis sort of experiment is basically the information that we covered, I want to say last Thursday. So if you want sort of a reference point in your notes or want to maybe go back and kind of look at the recorded lectures, we covered pretty much that stuff, I think, on Thursday's lecture. And then we also lectured last Thursday as well during lab time. So a lot of the pH and hydrolysis part of that was also in the lab portion, I think, on last Thursday. So basically, I believe, if I'm not mistaken, going off the top of my head, I don't have it right in front of me or anything like that because I'm looking at this screen, but I believe there's really kind of two parts to the pH and hydrolysis experiment. The first part is one where you'll have to kind of go through the different salts and try to decide, is it going to be an acidic salt? Is it going to be a basic salt? Is it going to be sort of a neutral salt? You'll have to write some of the hydrolysis reactions, which again is the salt plus water, which will either produce H3O plus on the product side, it'll produce OH minus on the product side. And you'll have to sort of make, I believe, technically, if you did everything correctly in the right order, you would do that first and kind of write those reactions, make those predictions in terms of, do you think it's going to be a certain pH or not. You then will, I think, sort of check it. I think there's a, if I'm not mistaken, a little bit different in this lab as well, is there's a kind of a lab simulation where you can kind of get the pH values and that type of stuff through it. So there is a link that will take you there to sort of the simulation web page. Now, I believe it's been a little bit since I clicked through it, but I believe one of the links will take you there. And then I think on one of the pages in the module, you also need to kind of go to, I think, that simulation, but it won't load in Canvas. So I think there's like an external link that will get you there that you need to click on when you do it. So I do know one of the pages, I think, is like that. So if you try to open in Canvas, it'll kind of say, hey, it's not going to work. But there is a link, I think, right above it where you can kind of click on it or either copy it to your browser, again, in a new window, and it should open up and stuff like that. So you do want to make sure you kind of watch the videos and all that, how to do this simulator. I apologize, I probably won't be too much help. I haven't really worked through the simulator all that much. So make sure you do at least watch the little instructions on how to sort of, go through it and get those values that you need. In part two, I think after you do part one, which is essentially that, you're kind of making some predictions in terms of is it going to be acidic, basic, or neutral towards of salts. Remember that if you come across a salt that has the ability to sort of go both directions, that's amphoteric. You could use the Ka value or the Kb value and compare them like we talked about to sort of decide, which way it will go. If the Ka is larger, then it would be the acidic sort of reaction you would expect. If the Kb is larger, then it would be the basic one. So I think there might be a couple of salts or something like that technically could kind of do either one. And you could again use, like we talked about in that lecture, the Ka value or the Kb value to sort of compare it to determine, which direction you would anticipate it going. So that's, I believe, the crux of pretty much part one of the experiment. In part two of the experiment, I did make a change, and I think I caught all the original sort of names, but originally in part B of the experiment, you were going to make ammonium chloride solution, and I think you were going to make a sodium hydrogen carbonate or sodium bicarbonate solution. So I think on the sort of simulator that you'll need to use for part B as well, it didn't really come out the way we would sort of expect. They kind of include some other sort of calculations that we don't talk about in this class. So I changed sodium bicarbonate in part B or part two of the experiment there to sodium cyanide, which I think will work better. So everywhere, if you may still come across some pages in the experiment that talks about sodium hydrogen carbonate for part B, again, wherever that is, maybe on a data sheet. And I think I try to go through and kind of change those sheets as well. But on any of those data sheets, if you see for like that part two, it says like sodium hydrogen carbonate. Again, it should be the sodium cyanide. You could just substitute for it. I think I went through and caught them all, but I might have missed some. So just in case you might see that, just change it for part B. So essentially, you're going to make two solutions, one ammonium chloride solution, one a sodium cyanide solution. You each should have an assigned molarity for each of those. So there's some different molarities given to different people. So you should have a file that you open that just kind of straight out says, for part B of the experiment, make this molarity of ammonium chloride, I think, and make this molarity of the sodium cyanide solution. And you also kind of work through the simulator, I think, in part B, if I'm not mistaken, and to make those solutions sort of virtually through the simulator, and I think also get like your pHs from there as well. So you'll have to make those. You'll be doing some dilutions of those solutions as well. So after you make them, you'll get the pH, and I think you'll do some serial dilutions to see the effect of diluting these salt solutions and the effect on the pH and stuff like that. And you'll get some pH values for those as well. So pretty much that's the experiment. And again, pretty much mainly focuses on salts and those hydrolysis reactions. So again, being able to correctly write those reactions. If you have a conjugate base, it will react with water and accept the H plus and produce hydroxide. If you have a conjugate acid, it will donate an H plus to the water and make H3O plus, and basically figuring those things out. In terms of the lab report for this one, we're not going to really type anything. You're just going to kind of fill out all the, I think they made a bunch of report sheets and pre-lab and post-lab sort of questions and stuff like that. So the lab report will essentially consist of what's up there. And I think they're kind of marked in terms of point values and all that kind of stuff. So you should be able to find them. But essentially, I think it should be the pre-lab question, I think, the post-lab questions. And then again, there's some data sheets to fill out as you're doing the experiment. And I think there's also some places to show some calculations as well on those sheets. So again, I think they set it up two ways. You could either sort of enter all that, I think, online and then upload it, or I think they made like a PDF file where you could, they made a PDF file where you kind of print it out, fill it out, and then upload that file. So again, you could kind of do it either way, but make sure you do submit all the parts, which I think are pretty clearly labeled in that module. but ultimately it should be, like I said, pre-lab questions, I believe, post-lab questions, and then those data sheets and calculations that they have you sort of fill out as you go through it. Any questions on that experiment? Yeah, so for the predictions, you're going to have to look in your book. Yeah, so it'll be kind of the same thing if we were in person as well. In person, you would typically go to the bookcase over there, that bookshelf, and grab an old book and find a KA table and a KB table. You should be able to find them in your book. There should be a KA table and a KB table, I think. I think your book has a pretty big sort of table. If not, you may have to look up those values in some other sort of resource, probably online as well. But I think the book should have most of it. Um, trying to think here. Yeah, you know what? For part one as well, I probably missed that one. You could change it. For part one, you could do one, two things. You could. It's okay for if you want to change it to sodium cyanide, you can. If you haven't done it already, if you've already done it with the sodium hydrogen carbonate, what you might see is that your predicted value might be different than your actual value. So that's okay too. So you could do it either way. So the reason for that again is because hydrogen carbonate is amphoteric, and there's some other sort of equilibrium involved that we don't really talk about in this class. So if you happen to have already done part one with it and it's maybe just different, it's okay. But if not, you can change it in part one as well to the sodium cyanide. I think that should work, I believe, if I'm not mistaken. But definitely for, I think, part two, you should probably change it for sure. All right, it's been changed, I think. Other questions? Okay, so that hopefully should take care of the lab. I think it's due sometime towards the end of next week. I may move it a little bit later, but tentatively, I think it's towards the end of next week is when that experiment is due, if I'm not mistaken. And again, today's experiment, again, was when it says due date and time, that technically is when it's due, like at the start of the lab. But it is available, I think, for today's until the end of the day at 11:59. It will let you upload it if you didn't get it in already. It will just mark it late, and I haven't decided, but I'm leaning towards that. I probably won't take anything off, probably, but at least if you get it in today. But it should still let you upload it even though the due date and time is passed, because the availability should still be there until 11:59 tonight, I think. So if you didn't get it in there, don't email it to me. Go upload it, yes, before today's over. All right. Any other questions on any of that stuff? Okay. All right. So we're going to continue lecturing, and we're going to continue here with buffers. So we're on this example here. So why don't you take a few minutes or so and kind of work through this. We're looking for two answers here. We're looking for what is the pH of this buffer to begin with. And then the second answer is after we have that buffer, what is the pH after we add 20 milliliters of 0.05 molar sodium hydroxide? So why don't you give it a try to make sure you sort of understand how to do this calculation. You should end up with, again, two answers. Here, though, we are not like the last one we did, assuming that everything remains the same volume. So you do have to incorporate these volumes into your calculations. So why don't you take maybe 5 or so minutes, 5, 7 minutes, kind of work through it, and then we'll see how everybody's doing, okay? So again, if you're just coming in, we're continuing on lecturing and we're working on this problem right now. In a few minutes, we're going to go over it. All right, so let us kind of take a look and see how we're all doing on this particular one here. Okay, so We are obviously told that it is a buffer, so that's a pretty big hint. Again, if you weren't told that, you hopefully at this point should start being able to sort of recognize these things as being related. Again, the ammonium chloride here is essentially NH4 plus and Cl minus. And again, it's that NH4 plus and that NH3. That's basically your weak base in this case, and conjugate acid combination that's going to make the buffer. So again, in this case, our buffer is going to be made out of the weak base and the conjugate acid. And that's fine because you can make a buffer again as either being acidic, basic, or neutral. So first question is really what is the pH after we add it and before we add it? So we're going to do the before part. So before we add the buffer, before we add the sodium hydroxide, in this case, to the buffer, we pretty much just have the buffer in there by itself, which means we could automatically go right into the Henderson-Hasselbalch equation. Because it is a buffer. Again, you could do an ice table if you wanted to, perfectly fine, but a lot quicker of a calculation probably in this case. Again, because it's a buffer and we can use the Henderson-Hasselbalch equation because that's essentially what it's for, we could go right into it. We do want to calculate the pKa value. Again, if it was not given to you, you would need to look it up. This is for our NH4 plus, which again, here, probably should grab my calculator, but I think it's 9.25. So minus the log of, we got there 5.6 to the minus 10. Yeah, 9.25 looks like a winner. 9.5%. And we do all that fun stuff there. We end up with an opening pH here for this buffer of 9.17. This demonstrates a couple of things before we get to actually the second part of the question. This demonstrates here very nicely that this buffer is actually a basic buffer, right? So this is a basic buffer, different than the one that we did in the previous problem, which was an acidic buffer. But regardless if it's a acidic or basic, this buffer, you can see that you can use the Henderson-Hasselbalch equation no matter what. Again, as long as you have the pKa value and you put the base on top or the acid on the bottom. This is a problem where, again, some people might choose to use that other sort of version of the Henderson-Hasselbalch equation, which is basically for the POH equals the pKb plus the log of the acid over the base. And a couple major differences would be you wouldn't look up your Ka value, you'd probably get your Kb value. That would give you your Kb, your pKb. And you would want to put the acid part on top in this case and the base part. Again, sort of the disadvantage of this is when you're all done, you still only have the POH, which then you need to take 14 minus the POH to get to the same number that we essentially got by just sticking it into the Henderson-Hasselbalch equation to begin with. So that's why I say, truthfully, you just use the Henderson-Hasselbalch equation. It doesn't really matter acid or base. And the nice relationship that we talked about as well is perhaps in this problem, if you were given the Kb value, you could get the pKb value from that, like we talked about, and then you could get to the pKa value by taking 14 minus it. So even if you were perhaps given this information, or you could only find this information, and that would be about NH3 in this case, there is still sort of a workaround that you could do to get you back to being able to use, obviously, the Henderson-Hasselbalch equation. So again, sometimes people use that top one, but I personally don't see the point in a lot of cases because usually you are asked, what is the pH? Very rarely in sort of buffer problems or even titration problems, you're asked what's the POH. So Works good for acidic, works good for basic solutions. Any questions on that? Okay, so let's talk about the second part. So now the second part is we're going to take this same buffer here. We're going to take our 0.3 molar NH3 and our 0.36 molar NH4Cl, which is our buffer, and we're going to add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of this buffer. So we have a buffer. We're going to add the strong base in this case to it. So we do need an ice table. And again, really the purpose of the ice table is to figure out how your buffer is changing when you add your sodium hydroxide to it. So in addition, we're also adding volume, which means when we do that ice table, we have to do it in moles, not molarity. So again, those are two important things to remember. Also, just as important is we want to make sure that we do get the correct equation going down. So let's take a look. So when we add our sodium hydroxide, it is going to react with, there's two parts to the buffer. There's again the base part, which is this guy. And there's the acid part, which is this guy. And when we do this reaction, obviously sodium hydroxide is a strong base. So when it reacts, it's going to react with the ammonium chloride in this case, which is our acid in the buffer. And when it does, we will get NH3, as it's going to again act as for our side, the moles would equal our volume of sodium hydroxide, which is 0.02 liters, converting our milliliters into liters. We're going to multiply it by the molarity of our sodium hydroxide, which is 0.05 moles. And for our sodium hydroxide, that's going to get us 0.001 moles. In addition, we also need to figure out the moles of everybody else. And we have our buffer. And for our NH3, we are taking 80 milliliters of our buffer, and we're going to times it by the molarity of our NH3, which is 0.3 molar. And that's going to give us our moles of NH3. And that looks like 0.024 moles. And lastly, we are going to get the moles of our NH4 plus, which would be 0.08 liters, which is our 80 milliliters, times the molarity of our NH4 plus, which is 0.36 moles per liter. And that's going to get us 0.0288. Make sure I did that right. 0.0288 moles of our NH4 plus. Any questions on those calculations? So again, we're just converting molarity and volume into moles. We want to make sure we're in liters to do that. And these are going to be our initial concentrations in our table here. So initially for our sodium hydroxide, we have 0.001. We got 0.001 moles. NH4Cl is NH4 plus, and that is 0.0288 moles. Again, because it's a buffer, we do have the guy on the right-hand side as well. So our NH3 is 0.024 moles. Water, not going to worry about, right? Not going to affect the pH. Although we got this third guy over here, also a neutral salt, not going to really mess with anything. So again, just like normal, probably shouldn't put any numbers in where you're not going to use them, so you don't mess anything up. Now our change parts, same thing here. We want to go with a smaller number, which in most cases with a buffer should be what you're adding. So in this case, it's the sodium hydroxide we're adding. Again, if we go with the larger number, we get a negative number, so we can't have that. So our change is going to be our sodium hydroxide here. Again, we're going to actually use the number, and we want to make sure we are adding on the other side. And that gets us to equilibrium, where that's going to zero out. Minus 0.001 gets us over here 0.0278 moles, and on the other side where again we are adding gets us 0.025 moles of our NH3. Any questions on the ice table here? Now, unlike the first example we did, we are not keeping the volume constant. So we do want to convert these back to molarity by using the total volume, which in this case would be 80 milliliters plus 20 milliliters. Gives us a total volume of 100 milliliters, which is 0.1 liters. So to convert these back to molarity, we're going to take each of them and divide by 0.1 liters. And that will give us the molarity of each of these guys. And we will end up with 0.278 molar for this guy. And 0.25 molar for the guy on the right-hand side. Again, as we talked about before, since we are adding volume, we want to do this first ice table in moles. Now, once you're done with the first ice table, very good practice to convert those moles back to molarity, because probably 9 times out of 10, you will need the molarity if you continue on with a calculation. Any questions on that? Now, a reminder that sometimes people wonder, why is the volume here 80 for both of these guys? And it is because it is a buffer. So when you have that solution, in that solution to begin with, you have the NH4 plus floating around, you have the NH3 floating around, and they're both in this same beaker to begin with. And again, this overall beaker was, say, 80 milliliters in this example. So that volume works for both components of our buffer because they're basically swimming around, in the same solution or the same beaker. Again, if you were completely lost at this point and not really sure what you got left at the end of this reaction, the ice table gives you an incredible amount of information. If you go back to your ice table, you could clearly see, hopefully, that when you reach equilibrium, these are the two guys that you have, the NH4Cl and the NH3, which should again spark in you the idea that they are related to each other and you still have a buffer going on. And that's going to help you decide how to finish this problem. So to finish this problem, you do have two options. You could go into the ice table, but I'm going to go into the Henderson-Hasselbalch because this is still a buffer at this point. And because it's the same buffer with the same weak acid, the Ka value is still the same, which means the pKa value is also still the same. In this case, we want to get the base part on top. I'm going to try this right this time. We're going to go with the NH3, which is our base. And that's going to be 0.25. And our NH4Cl, which is really NH4 plus, is our acid, which will go on the bottom. And let's see how we did here. 0.25 divided by 0.278. Do a little bit of log. Add it to 9.25. Going to give us a 9.20 in terms of our pH. And you could see that this buffer did work, right? So this buffer worked pretty good. We started at 9.17. We added some base. It went up to only 9.2. It also went up correctly because we added base. So we would expect the pH to go upwards, which it did. Again, these are ways you could check yourself when you're done with the calculation to make sure that you didn't kind of mess up anywhere on that. Any questions on that there? Okay, any questions on buffers or how to calculate buffers? Let me just talk about one more thing about buffers just to illustrate what we were talking about earlier today. And just find a spot where I could scribble. Done a lot of scribbling apparently. Actually, let's see this buffer. We'll take a look at this buffer real quick here, just to kind of illustrate. So this is the one that we did earlier with the acetic acid. And just to illustrate the idea of sort of buffer capacity and why it's important, for example, the molarity of the buffer versus, say, the molarity of what you're adding and why it's extremely important. So let's say we took the same 1 liter buffer solution like we had here. So we'll still take the 1 liter buffer solution just like we did here. Now, instead of adding 0.1 molar HCl, let's just say you forgot and you did not read the instructions very well, and you decided that you're going to add 1 liter of 18 molar HCl to this buffer. Yeah. We'll just go with the extreme here. Yeah. So we're going to get the same reaction that's going to occur. We're going to get our HCl that we're adding. And that is going to react with the base part of the buffer like we did in that problem. And we're going to get the same reaction as what we saw earlier, which is acetic acid plus our sodium chloride, right? Now, because again, we're adding, we do want to do this in terms of moles. So just like we did here, we had 1 liter of each of these. So that is going to give us 1 moles here. And it's going to give us 1 mole here. But now you grab, say, this bottle and put a ton of it in. And when we get the moles of our HCl in this case, this would give us 18 moles of HCl, right? 1 liter times 18 molar is 18 moles. So now when we put that into our initial table over here, when we come to the change part, we could clearly see that this HCl is no longer the limiting reagent in this case, if you want to think about it that way. We have now just turned our sodium acetate into the actual limiting reagent, which means the change here is actually not going to be the HCl. It's going to be the sodium acetate in this case, because this buffer only had 1 mole of sodium acetate to take care of all the HCl that you put in there. And you essentially just used it all up by adding way too much in terms of concentration of that HCl. And what you'll end up with on the equilibrium line is you'll actually end up with 17 moles of HCl. You would have used up all of your sodium acetate, and hit a button. There you go. And coming down this way here, you would end up with actually 2 moles of acetic acid. So in this particular solution, you could convert these to liters, to molarity. But what you would actually have left in this solution after you added that is you would have a bunch of HCl that's going to break apart, and you'll have some weak acid that will stay together but break apart a little bit as well. And this is why when we add sort of the wrong amount of a strong acid or strong base to a buffer, our buffer is not the right molarity to handle what we're adding. What we've just done in this case is generated a bunch of free H pluses, because essentially we blew right through our buffer capacity in this case, because ultimately, as we can see from these calculations, these buffers only have a specific amount of moles of their weak acid and conjugate base, or their weak base and conjugate acid, to react with whatever strong acid or strong base that you're adding to your buffer. So this demonstrates that if you sort of choose wrong in terms of the concentration of your buffer, or wrong in terms of the acid that you add or base that you add to your buffer, you can blow right through it, and you will end up seeing, obviously in this case, the pH would go way down because we've now made a bunch of free H plus in this case from this reaction. So basically, that's sort of the calculation that demonstrates what we saw earlier, where I drew it somewhere, where I drew this part here, where you just keep adding acid, or you add the wrong amount of acid, you're essentially just going to blow right through the base part, and all you'll be left with is the acid from the buffer and the strong acid that you're adding. And as you can see here, obviously that would create a giant concentration for our HCl, which would get you something in a negative pH, like negative 1.23, which means it's like a super acid. Yeah, if you take the minus the log of 17, it's like a minus 1.26. That's like super acid type stuff. Very strong, very, very strong. Although so strong, we don't usually deal with negative pHs. Technically, you can have a negative pH. You can, but it's obviously very, very strong. Any questions on that? So again, that is just sort of the calculation-based way of demonstrating that there is a limit to how effective a buffer can be. And usually, again, the effectiveness of the buffer is within what we were talking about earlier, that plus or minus 1 of the pKa value. So plus or minus 1 in terms of pH and that pKa value. Again, if you chose the acetic acid as your buffer component, it would be 4.74. So it's most effective plus or minus 1 of that 4.74 number. Again, as you get outside of that range, it's not going to work as well in terms of sort of being efficient and as being a buffer. Any questions on buffers or any of that type of stuff there before we move on to the next major topic? Okay. All right. So the next major topic, and again, the good news is we're sort of nearing the end of the most difficult parts of this class, really. So buffers was one major part of the class that gives people a very tremendously hard time. The second sort of part that gives people a hard time is titrations. And in a titration, you probably have done it before. We usually will add a solution using a burette of known concentration, for example, to a solution of unknown concentration. And that will allow you to find certain things out, like you could find the molarity, for example, of the unknown solution by using stoichiometry and molarity and volume. You could also find out how many grams, for example. You can find the molar mass. You can do a lot of things. You could also do it backwards and figure out what the molarity of what you're adding is. We add from a burette to a flask, usually, like the picture shows here. And we continue to add until we reach what is known as the equivalence point. The equivalence point in a titration, especially an acid-base titration, is the point in the titration where you are exactly at the point where the moles of the acid will equal the moles of the base. So that truly is what we mean when we reach the equivalence point. It means that at that particular point, we have added the exact same amount of moles of acid to base. So how do we know when we sort of reach the equivalence point? And usually what we use is a indicator. And probably the one we see in this picture here is the most popular one that you probably have used before, phenolphthalein. Phenolphthalein is an indicator, but indicators in general, they change color so that we can visually see that we should stop our titration. When we pick a indicator, it is very important to pick an indicator that will actually change color near your equivalence point, because that's the whole point. Usually when you do a titration is you want to get to that point where you have basically kind of neutralized it, if you will, used up all of your moles of acid and all your moles of base. For example, phenolphthalein, which I will spell like normal. No, I'm just kidding. Phenolphthalein. Looks just like that. There's some other letters in there, which I don't remember right now, but you get the idea. When we talk about that in acidic solution, as you may know, phenolphthalein is colorless. In neutral solutions, as you may guess, I'm going to help you out there. No, it's not pink. It's actually colorless as well. It's really not until you get to basic solutions that we see our classic pink color. And as we'll talk about here towards the end of this chapter, the way indicators work is they essentially work over a pH range. So for example, something like phenolphthalein, I guess I should pick the right color here. I'm going to demonstrate that, I suppose. We'll go with pink. Phenolphthalein works over a pH range of like 8.3 to like 10-ish. And around 8.3 or so, it's colorless. Then as you head towards 10, you get everybody's favorite dark, beautiful color, right? And this is why, if you've ever done a titration before, which I'm assuming you have, they often will tell you when you use something like phenolphthalein, what you're looking for is the first pink color that stays. So pink in color, or so light pink in color, really. So light pink in color that you almost got to put some white piece of paper underneath it to kind of see the pink. You're actually, in most cases, when you do a titration that you've done in the past, you're not really shooting for this really dark, super dark color, or fuchsia color, depending on how far you go. You're actually looking for that first, like, barely sign of pink that stays. And the reason for that is, in most titrations, as you probably have done before, it involves acetic acid, which is vinegar, for example, and sodium hydroxide, which means the equivalence point in that type of titration is probably in the pH range of 8-ish. And that's why they yell at you, hey, you should have like the barely color of pink, because that will put you more at the 8.3-ish range and closer to your equivalence point. Then once you kind of shoot to that really dark pink color, you're at least heading towards that 10-ish pH, which means you potentially could have really went way past the equivalence point. So that's usually why they yell at you, light, super light. You can barely see the pink color. We will also answer the age-old question when we talk about titrations here of what you commonly hear when people do titrations. And they commonly say this, usually when they get close to that equivalence point, I don't understand it. I only added 1 drop. And it went from like colorless to super pink, right? And you're like, hey, I only added 1 drop. It went crazy on me. And we're going to explain why that is actually as we start talking about here, the titrations, why when you add only 1 drop, you can potentially sometimes see that big jump in pH. Now, another word that you sometimes will hear when you're talking about titrations is what is referred to as the end point of a titration. And the end point in a titration is essentially what the name sounds like. It is pretty much where you lay up and go, I'm done with my titration and I'm finished. Ideally, if you do a good titration, your end point in your titration, where you stop, and the equivalence point should technically be pretty close to each other if you did it sort of correctly. If you did it incorrectly, you just opened it up and wait for dark pink and call it a day. Yeah, you'll be okay. You'll be done with that titration very quick. Any questions on the basis of titrations there? All right, so we're going to talk about some different types of titrations that occur when we come together with a strong acid and a strong base, or we come together with a strong acid and a strong base and a weak acid. And if we come together with a weak base and a strong acid. So let's take a look at that then. So the first type of titration we're going to look at is a titration between a strong acid and a strong base. So in this titration, we're going to take hydrochloric acid. We're going to react it with sodium hydroxide. And we're going to get an acid-base reaction of some water and a little sodium chloride in this case. So just so everybody is visually understanding what's going on here, let me draw my classic burette, which kind of looks like an arrow. We'll put the little stopcock on there to open it. So up on top in our burette, in this case, is the sodium hydroxide. In our beaker, in our flask, we are adding to it the HCl. So in this case, we're adding the sodium hydroxide to our HCl in this particular case. What you see on the graph is what is known as a titration curve. On the left-hand side, or the Y, we have pH. On the X, we have the volume, in this case, of sodium hydroxide that we're adding. And this is what is referred to as a titration curve. And this curve here is a typical titration curve that you see. You sometimes will see, again, this sort of S curve that occurs. So let's talk about each of the parts here of this curve. Let's start with the first part, which is way over here. So before we add any sodium hydroxide in this case, and if we want to calculate the pH, all right, so we'll go here, I guess. Before we add any sodium hydroxide, if you think about what is in that solution before you add any sodium hydroxide, what you would have is just your HCl solution. So as you can see on the right-hand side there, before we add any sodium hydroxide, the only thing that we have in that beaker is the HCl. And if we wanted to figure out the pH before we begin the titration, we basically have HCl in this case, which is a strong acid, And because it's a strong acid, it will 100% break apart into H plus and Cl minus, which means, as we talked about earlier in this chapter, from that we could get the concentration of H plus and then go directly into our pH equation. And we can get the initial pH of this solution before we add any sodium hydroxide to it. So again, if you start in this titration, you could get the opening pH before you start it by just taking the strong acid and going right into the pH equation, because that probably will be the H plus concentration. Also, in this case, we have not started adding any sodium hydroxide to it. So you're good to go with the molarity here of your HCl. In this particular example, again, we haven't added any volume, so we don't have to worry about doing it in moles or anything like that. So that would be how you would get the pH at the very beginning of the titration. Now, if you decide, all right, I'm going to start the actual titration, give it a go. Anywhere in this part of the curve, anywhere in this part of the curve where you start to all the way before you reach the equivalence point, you're actually going to start the titration. And when you start the titration, you will actually need to do an ice table. But now at this point, because we are adding volume of sodium hydroxide consistently in this reaction, we are consistently changing the molarity. So this is definitely a place where you're going to have to do the ice table in moles. So you will have to do that ice table in moles because we are adding volume. So let's take a look at that. I'm just going to flip the page and we'll come back to this picture in just a second to continue on looking at it. Now, so let's say we are started the titration, but before the equivalence point. Okay. So EP equivalence point. So before the equivalence point, but we have started adding, you will need to do an ice table. So that ice table is going to be the reaction in this case of our strong acid plus our strong base. And it's going to give us some water and some sodium chloride. Yeah. All right, so we want to do this ice table in moles. All right, so just to be clear, I am going to put some numbers into this table, and these numbers are just numbers I made up, okay? So these are just numbers that I made up. We're going to say that we started with 4 moles of HCl. Again, I made up the 4 moles, just randomly picked it, no significance other than I made it up. And basically what that represents is that is how many moles of HCl are in our beaker to begin with before we start the titration. Now, when we start the titration, because we are before the equivalence point, should the moles of my sodium hydroxide, which is what I'm adding, be greater than, equal to, or less than my moles of HCl? So the answer is because we are before the equivalence point, because at the equivalence point, the moles of acid and base equal each other. We have not got there yet. So what that means is before the equivalence point, the moles of my sodium hydroxide should be less than the moles of my HCl in this case. Again, I'm just making this number up. I'm just going to say 2 moles. The rest of the ice table would be 0. Again, I'm not going to play with water because it's not going to be involved in anything. But we should have less moles of what we're adding to what we started with because we're before the equivalence point. The rest of the ice table will be very similar to what we were doing with the buffers. This now becomes our limiting reagent because it's a smaller number. So minus 2, plus 2 moles, which will get us at equilibrium 2 moles of the HCl, 0 of that, and 2 moles of that. So this table is very much like the one that we just did. Just like most of these tables where you do moles, at this point, you would want to go back, not the page actually, but you would want to go back and divide these guys by the total volume in liters. So again, this is our total volume. And that would obviously be how much you started with in terms of volume and how much you added in terms of volume, right? And that would get us the molarity of this guy. That would get us the molarity of this guy. And again, if you look at your ice table, you have HCl and you have sodium chloride that is left over. Let's talk about these two things. Is this a buffer? You do have two things. They are related to each other, and you do have two numbers. So you might be tempted, hey, I'm just going to go into my buffer equation. Everything's good. And if you do that, this is what you'll get, a big X, everything not so good, because these two things, although they are related to each other, that's an acid, that's a conjugate base to Cl minus. The problem, though, is this is a strong acid, which, as we were talking about, you cannot have a buffer made up of a strong acid. So really what you have here is a strong acid, which is going to affect the pH, right? Going to affect the pH. And we also have this guy, which is a salt, right? And that is sodium chloride. We also talked about salts as well. Sodium chloride is a group 1, and chloride, this is a neutral salt, right? So this salt, which is made up of sodium, which is group 1, has no effect on the pH, will not go through hydrolysis. Cl minus, which comes obviously from HCl, is relatively weak and will not go through hydrolysis. So although we have a number here, not going to affect the pH, which is why you might not want to include it in your calculations or your table, because you might want to use it somewhere. So really what we're left with at this point is a strong acid in that solution. So since this is a strong acid, at this point in the titration, we then can go right into the pH equals minus the log of the H plus. So once we start this titration, it's a little bit different of a calculation. You are required to do at least one ice table, kind of like what we did up on top. The whole purpose of that ice table is to figure out the new concentration of your strong acid. And once you get the new concentration of your strong acid, then you could go directly into the pH equation, and that would get you the pH of that solution at that point in the titration where you stopped. Any questions on that there? So that takes us, if we come back to our curve, all the way up to our equivalence point. So let's talk about what happens when we actually hit the equivalence point in this type of titration. So when we hit this equivalence point right here, that again means that the moles of the acid should equal the moles of base in this case. So when we hit the equivalence point, let's take a look at a calculation to kind of determine what we would expect to happen. So we're going to take our same guys here. And we're going to talk about what happens at the equivalence point. So you will still could look at it through an ice table. So if we make an ice table just to visually see what's going to go on, we have our same reaction. And again, here we're going to do an ice table. It again is going to be in moles. So again, I'm just going to use that same number that I made up. We're starting with 4 moles of HCl. And in this particular case, since we are now at the equivalence point, we should be able to make a determination of how much sodium hydroxide we added. So since basically the definition of equivalence point is the moles of the acid will equal the moles of the base, we know right off the bat that the moles of sodium hydroxide here should also be 4 as well. Any questions on that? So again, because we're at the equivalence point, exactly at the equivalence point, we know that the moles of each of these guys should be the same of what we are adding, which is the sodium hydroxide in this case, to where we started, basically. That means you really can't screw this up, hopefully. There's only one number to choose from. The change in this case should be -4, and a +4 on that side. That means when we reach equilibrium, 0, nothing. We have 4 moles of this guy. Just like before, you could use the total volume here and convert it into molarity. And again, as I've been sort of stressing, the actual ice table is very important. It gives you a lot of information. We could see that at equilibrium, the only thing that we got left is sodium chloride in this case. And sodium chloride, as we know, is sodium ion and chloride ion. So as we just talked about up there, we know sodium, which is group 1, will not go through any type of hydrolysis. It's weak and neutral. We also know chloride that came from the HCl is weak and will not go through hydrolysis. It is also neutral, which means in reality, when you're at the equivalence point in this type of titration between a strong acid and a strong base, the pH at the equivalence point is always going to be a pH of 7. You actually don't even need to do the ice table. You don't need to do the calculation, because in reality, no matter what combination of strong acid and strong base you put together, you will always produce a salt that is neutral. And this is why when we look at our titration curve, coming back here, and if we followed it over at the equivalence point, we could see in their example, the pH at that point is going to be 7, because you will always, at this point in this type of titration, produce a neutral salt. Any questions on that part of the titration curve? Now, before we go past the equivalence point, let us answer the question that, again, a lot of people have when they do titrations, or what commonly people will say is, I don't understand. I only added basically 1 drop of my sodium hydroxide, and my pH went from, I'm sorry, not my pH, but my solution went from basically no color to solid pink. And that is because when we look at this curve, as we approach the equivalence point, what we see happen, and even as we go past the equivalence point a little bit, what we see happen is it is a basic vertical rise. And what does that really mean? What that means is, because it's going vertical, my pH is going up. So our pH here is starting to go up. But what it also means is if I'm going vertical, as bad of a straight line as that was, my volume is not changing very much. So my volume is not changing very much. So basically what happens as you approach the equivalence point is the pH will start to change relatively rapidly with very little, in this case, sodium hydroxide, for example, added. And that is why when you do that one drop of sodium hydroxide in your titration, and you've seen it go from like dark, no color to dark pink, by adding that one drop, that is not a lot of volume per se, but that little bit of volume is enough to change the pH. So even though you added a little drop, that's enough to make the pH start to rise. And again, if you think about phenolphthalein, kind of 8.3 in this range, like 10-ish in this range. So even though you technically added only one drop, it was enough to move that indicator and the pH upwards in this direction. And what you visually will see is it start to become darker pink. We'll pretend the green is pink here. It goes darker pink in that case because the pH changed a lot, even though you didn't add a lot of volume. That is also why when people yell at you that you should get it to the lightest color of pink that you can get, they are correct. You should do that. But the reality of it is this: if you really only miss the equivalence point by 1 or 2 drops, it's not going to make a tremendous difference in any calculation that you do. Just visually, it's going to look darker, but it actually won't make that big of a difference. Now, don't get me wrong, if you opened it up and just way went past it and added a lot more volume, it will definitely mess up your calculation. But if you're really careful and you're titrating, you just added that one drop and it went super pink, or maybe 2 drops or 3 drops past and it got really super pink, you probably are not that far away from the equivalence point in terms of volume. And it probably would not make a tremendous amount of difference in your overall calculation. But again, if you did open it up and put a ton of sodium hydroxide and went way past it, it would make a difference in the calculation. Because again, this is why when we add just a 1 drop and it goes from a big color change, it is because as we approach that equivalence point, we go vertical, which means the pH changes a lot with little volume added. Any questions on that? So we also will see that sort of vertical leap past the equivalence point. So usually as you're doing a titration, if you're following the pH, you'll see sort of a big jump to the equivalence point. And then you will also see usually a big jump in pH going vertical after the equivalence point as well. And then it will start to kind of level out at some point. You usually get like a pH of 12-ish or so. It'll start to kind of level. So let's talk about what happens in this part of the curve after we go past the equivalence point, because you're doing the titration and you're not going to be stopped by that color change. You already went dark pink. Why not keep going? So if we go past the equivalence point, using our same example here, you would have your same reaction of your HCl and your sodium hydroxide. Gives you some water and some sodium chloride. Again, using my same made up example of 4 moles of HCl to start with in our beaker. Now that we are past the equivalence point, what we should know is the moles of sodium hydroxide, which is what we are adding, should actually be more than the moles of HCl that we started with. Because again, at the equivalence point, Those guys are equal. So they're equal at the equivalence point. So when we go past the equivalence point, essentially what you're doing is just dumping a whole bunch of base in there, right? So again, I'm just going to make up a number here for sodium hydroxide. I'm going to call it 6, which is more than 4. Now, the same thing happens here that we talked about when we added way too high of a concentration of acid to our buffer. There is a switch that occurs in terms of the change part. Because originally in our beaker, we only had 4 moles of HCl to react. When we add 6 moles of sodium hydroxide in there, we have now made our sodium hydroxide kind of our excess reagent, if you want to think about it that way. And our HCl becomes our limiting reagent, which means the change part that's going to occur is actually the HCl in this case. So that's going to be minus 4, and plus 4 in this case. Which means when we reach equilibrium, we would have used up all of our HCl. We will have 2 moles of this guy here. We'll also have 4 moles of this guy. Using our total volume, we could convert each of these back into molarity. And again, in terms of the selection, also think logically about it. You can't have a negative moles or concentration, so you've got to always take the smaller number when you do the difference. And if we look at our ice table, we see that we have sodium hydroxide that is left. We have sodium chloride that is left as well. Those two things are not related to each other. So they are not related to each other. So we basically have 2 things. We have sodium chloride, which, as we talked about a number of times at this point, we know that this guy is a neutral salt. Will not have an effect on pH, so you don't even need to worry about it. Again, you could almost leave it out of your ice table if you're concerned you may use it in the wrong application. What we are left with, though, is sodium hydroxide. And sodium hydroxide is a strong acid, which means essentially this will equal our OH minus concentration. And remember that that's your OH minus concentration, which means it's not a strong acid. Sorry again, just a strong base. Thank you. That will give us our OH minus concentration, which allows you to calculate the POH first. And then you can take 14 minus the POH to get to the pH of this solution. So when we go past the equivalence point, you do have to do an ice table. The whole purpose of the ice table is to figure out the concentration of your strong base that you have left over. Again, because essentially you're just dumping in base in this reaction. Once you do so, that will give you your hydroxide concentration, and that will allow you to calculate the pH of that solution at that point. And that's why when we look at the curve here, we see a jump in pH, because essentially you're just adding a lot of strong base, which is going to generate a lot of OH minus, and that OH minus is going to make the solution go basic. So you need to be able to calculate the pH anywhere along this titration curve, or everywhere, if I'm mad at you guys, I suppose, all 132 points. No, you do need to be calculate all the points anywhere along the way. Again, before you begin, it's just a strong acid problem right into the pH. As you begin the titration before the equivalence point, you need at least 1 ice table to calculate the concentration of your acid that's left over, and then you can go into the pH. At the equivalence point in this type of titration, you do not even need a table or a calculation. You pretty much could just put a pH of 7 and move on, because it will always generate that strong, that neutral salt. Going past the equivalence point will require 1 ice table. The purpose of the ice table is to figure out the concentration of your strong base, and then you could go into the POH and then into the pH equation or figure out the pH from that. Any questions on any of those there? So why don't we try one just randomly here? Let's take a look. We'll kind of look at the one that we were in that graph there. All right. Let's say we were doing the same titration as in that curve. We'll do some real numbers so you can put them in to make sure. So let's say that we started with 25 milliliters of 0.1 molar HCl. What is the pH after we add let me see which one I want to do. Okay. After we add 23 milliliters of 0.1 molar sodium hydroxide. So take a moment and calculate that. I'm going to do it as well since I just made it up. We'll talk about it in about 5 minutes or so. So figure out the pH in this part of the titration. Okay, so let us take a look and see how we're doing here. So we're doing basically the same titration as we've been looking at in this titration curve. So again, the sodium hydroxide is up in the burette. The HCl is in the flask, flask or beaker, and we're adding the sodium hydroxide to the HCl. So again, we are going to have a reaction that takes place. We obviously have started the titration, so that is going to require us to do an ice table. So it's going to be the same reaction that we've been talking about for this particular titration. Again, here we are definitely adding volume. So we want the moles of everybody here. So the moles of HCl is going to be found by converting our milliliters into liters. So that would be move the decimal place 3 places to the left or divide by 1,000. Gives you 0.025 liters. We're going to take the molarity, which is 0.1 moles per liter, and that will get us moles for the HCl of 0.0025 moles of HCl. We're going to do the same thing for our sodium hydroxide. We're going to convert the volume into liters by dividing by 1,000. That gets you 0.023 liters. We're also going to multiply it on a curve by the molarity, which is 0.1 moles per liter. Again, our liters are going to cancel, and that will get us a opening moles of 0.0023. Any questions on that calculation? So again, we definitely want to make sure, usually in any titration situation, when we're doing an actual part where we're adding, that we do it in moles. So this is going to be our initials when we come to our table. So initially we got 0.0025 moles of our HCl. We got 0.0023 moles of our sodium hydroxide. Again, we have 0 here. Now, again, it's very important to understand sort of where you are in the titration so that you can kind of know if whether or not perhaps your answer makes sense or you're kind of on the right track. Again, if we look at our HCl, that is what we started with in the beaker. Our sodium hydroxide, again, is what we're adding. When we do a comparison of the moles of each of these, we see that we have more moles of what we started with to less moles of what we're adding. Or the other way of saying that, I guess, is less moles of what we're adding to more moles of what we're starting with. And what that should tell you is, in terms of where you are in the titration curve, is you should be before the equivalence point. Again, we know at the equivalence point, like we talked about up here, the moles of the acid would equal the moles of the base, which is not the case here. It's close, but not the case. But we do see that what we started with, which is the moles of the acid, is actually more than the moles of the base. So that tells us that we are before the equivalence point. Remember, the opposite occurs, just like it did up here, that when we're past the equivalence point, we actually have more moles of what we're adding than what we started with. And again, that's opposite of what we have here. So this will tell you that you're before the equivalence point. It will also help you make that decision if you're not sure that the change part here should be the sodium hydroxide, because you're before that equivalence point. It is still the limiting reagent, and we would end up with 0.0023 minus 0.0023 and plus 0.0023 if you put something there. That means at equilibrium, we will have, in terms of our HCl, not a heck of a lot left, I think, but we will end up with 0.0002 moles. We'll end up with 0, this guy, 0.0023 moles. At this point, we do want to convert back to molarity. And at this point, the total volume is going to be the volume that we started with, which was 25 milliliters of the HCl. Then we added 23 milliliters of the sodium hydroxide. That's going to give us 48 milliliters as our total volume at this point in the titration. That means that we technically would divide this guy by 0.048 liters. We would divide this guy by 0.048 liters. And if we do that for our HCl, you'll get 0.00417, taken into a couple of digits, not rounding too much here yet. 0.00417 molarity, and 0.0023 divided by 0.048 would get you 0.0479 molar. Any questions on sort of the ice table or anything like that up to this point? All right, so again, the ice table, very helpful to help you decide what's going on. At this point, in terms of equilibrium, we have sodium chloride, we have HCl. So as we talked about earlier, although they are related to each other, they are not a buffer because, again, HCl is a strong acid. We also know that the sodium chloride is a neutral salt, which means we don't even need these numbers. That means really what we're left with here at this point in the titration is a strong acid, which is what we would expect since we are before the equivalence point. And that means that really, since this is HCl, it's monoproduct. That is my H plus concentration, which means I now could go directly into my pH equation with my new concentration of minus the log 0.00417. Gets me a pH of 2.38 at this point in the titration. And we can maybe check ourselves. We'll take a peek back at that table or the chart. So we were at 23, which is in this area. And we ended up with 2.37, which is, or 38, which is higher than 2.2. We actually are less than the 2.69. So it probably makes sense, our answer that we got there. Any questions on any of those steps there? So a couple things before we finish up here, just to make sure everybody's very clear in terms of what we're talking about here. All the calculations that we have just talked about for this titration is specific for a titration between two certain things, and those certain things are a strong acid and a strong base. So these calculations and how we did the calculations are specific for this type of titration, which again is only a strong acid and strong base. We are going to talk about two other types of titrations where you take a weak acid and a strong base, and also where you take a weak base and a strong acid. They have some different calculations involved in them. So again, what we just went over here, specific to one type of titration when you're titrating a strong acid and a strong base together. Any questions on that? Now, another important question is sometimes people have when we deal with sort of titrations is, we'll just kind of look at the curve here. In titration problems, you are sometimes asked, like, what is the pH in multiple places down the road? Like, for example, you would be asked, what's the pH after you added 5 milliliters? What's the pH after you added 20? What's the pH after you added 28 milliliters? And you'll get a question where they will ask you all these things, obviously, in the same question. And when we talk about sort of the volume that's happening in that type of question, the volume is the total volume at that point. So you want to treat each of those questions separately. So, for example, when I would do the first question about 5 milliliters, the total volume of sodium hydroxide would be 5 milliliters at that point. When I go to the next part of the question where it asks, what is the pH after 20 milliliters of sodium hydroxide is added? When I'm doing the calculation for 20 milliliters of sodium hydroxide, that means I've added a total of 20 milliliters at that point. Not that I've added 20 plus the 5 I did in part A for 25 milliliters. So basically what they're saying is in those type of questions is as you go from this point to this point, you technically added 15 milliliters for a total of 20 milliliters at that point. So usually in a multiple sort of calculation problem, which is very common with titration problems, you treat each one separately, like you started at 0 each time. With the burette, you opened it up and you shut it exactly at 5. Then you technically for the next one started at 0, opened it up, shut it at 20. Next one, you started at 0, you opened it up, you shut it at 28. So sometimes people, for some reason, want to always, when they have multiple parts and like a titration problem, want to continuously sort of add the volumes together as they're going. But usually when you see a number, it means that you kind of can think about it. You started at 0, you opened it up and stopped at that volume. Any questions on that? That should allow you again to be able to obviously calculate the pH anywhere along this curve if you're given enough information to do so. Any questions on any of that stuff here that we talked about in terms of titration so far? All right, I think that's probably enough torture here for one day. So at least we got into some titrations. We will on Tuesday obviously talk about the other two types of titrations, which again is a weak acid and a strong base titration and a weak base and strong acid titrations. We'll see how they're a little bit different. So hopefully on Tuesday we'll wrap up the rest of that, which should also wrap up chapter 14, I believe, at that point. Then we'll probably, hopefully, maybe roll into 15. We'll be sortish on track. Again, we're probably going to be moving everything down one day and everything like we've been doing. The next exam will be chapter 14 and 15. 15 is not a very long chapter. So I would anticipate sometime by the end of next week, we should be pretty close to finishing chapter 15 as well. So it's not a lot in that chapter. Any questions on any of that stuff? All right. So, like I said, I'm probably going to stop for today at this point. Like I said, you should already be able to kind of be working through the pH and hydrolysis experiment. We definitely have covered, I believe, everything that's in there. Make sure you do watch all those videos and sort of links of how to use like the simulation software and all that kind of stuff. Again, I'll be truthfully honest with you. If you email me how to do something with that simulation software, at this point, I'm not that truly familiar with it. There'd probably be a lot of help to you. So make sure that you do sort of follow the instructions and the videos and stuff like that. And again, a reminder that I think one of those you do have to sort of click out of Canvas through the link to get it to load and work. Yeah, if you need help, you could email me. Yeah, I'll be here for probably another maybe 30 minutes or so, I think, a little bit. If you do have some questions, what I'm going to do though, I think, is I'm going to stop this this meeting now. That way this recording won't have all that dead air to have to edit out later. And then I'm going to reopen the same meeting, and you'll have to, if you have questions, come back through the same link that you use for this meeting right now. But I'm just going to stop this one. So we'll stop the recording. So that way I can post this with the kind of the lecture part kind of separate from any questions and stuff like that. So What I'm gonna do is stretch, and you probably might want to stretch as well. So I'll stretch, and maybe in like 10-15 minutes, I'll reopen the same meeting. And if you do have questions, you can come back in and ask, and I'll hang out for a little bit to answer those. And then, like I said, if you have other questions along the way, you can always email me as well. Any other questions on anything? Okay. Have a good weekend if you're out. And like I said, I'm going to stop this one right now, but I'm going to reopen it in probably like 15 minutes for just a little bit.